Okay, hi. Today I'll be talking about ODEs, and I'm Natanya Tabar Domingo. So today's lesson we have introduction, types of ODE, methods, industrial application using ODE. Introduction, we have example for separable differential equation, which is a method to solve it. We also have Gottfried Wilhelm Leibniz. He invented Leibniz notation, which is dx dy. We also have Isaac Newton, which contributed development of ODE very much, and he's also considered father of ODE. ODE are equations that involve a function and its derivatives, and they are mainly used in modeling. But I'll be talking about order, linearity, and homogeneous linear ODE. Order, so the order of a differential equation is defined to be that of the highest order derivative it contains. So linear. A linear ODE equation is linear if it has this form, and it's also linear if a dependent variable and all of its derivative appear in the linear fashion, and also if it's not multiplied by squared or with sine or cosine. So homogeneous linear ODE. ODE equation is homogeneous when Rx equals to 0 and vice versa. And to solve a non-homogeneous ODE, it's you gotta make it exact and also multiply both sides by integrating. Methods, we got separation variables, integrating factor, exact equation. So separation variables, first you gotta rearrange the equation and put all the y in the left and all the x in the right, and then integrate both sides in terms of y and x, and then simplify it in terms of y. Integrating factor, this approach applies to linear first order equations only. uh, First you gotta identify the integral factor like fx, then multiply it with both sides of the equation as mentioned in the previous part, and finally integrate both sides to find the variable. Exact equation, to do this one you gotta find out if the equation is exact and then use the exact equation formula. So first you put the equation all to the left side, equate it to 0, and then differentiate m and n in terms of dx and dy, and then if it's exact, if it's equal to each other, it's exact. Industrial application using ODE. So I use chemical reactor dynamics industry. This is a great example of how ordinary differential equation ODEs are used in industry, in chemical engineering, particularly in designing reactor CSTR reactors. For first order reaction, the rate of change of concentration of reactant inside the reactor can be described by the following ODE. This equation for this modeling, where CAT is equals to concentration reactant at time t, and K is rate constant of the reaction. So to solve it, you gotta use separation of variables, and then you'll get this certain equation. So Ca0 is equals to initial concentration, so at time 0. E to the power of negative k times t is the exponential decay term, where k is the rate constant and t is the time. So here we're gonna be calculating the concentration at time 10 minutes. So just key in all this. If we key in all this, after 10 minutes the concentration of the reactant is 0.3679 mole per liter. That's all from me for today, and thank you for watching.